We now know what independence means for events and for classes of events, but we'd like to understand what it means for random variables to be independent. In previous cases, where we have some property of events that we'd like to extend to random variables in an appropriate fashion, for example, extending probability measure to expectation or integral, we would start with indicator functions and generalize to simple functions and generalize to measurable functions. We could view what we're about to do in that framework, but instead we're going to be a little more functorial and notice that, hey, we know what it means for sigma fields to be independent, and associated to each random variable we have a sigma field, the sigma field minimally measurable with respect to that random variable. And so that leads us to the simple definition of independence of random variables. Suppose that we have a collection of random variables, and in fact, we can be very general here and allow them to take values in any state spaces that we want. So let xi be a collection of measurable functions defined on a common probability space, taking values in some state spaces. Now, the most common example we'll be dealing with is where these are all of the form r di with respect to the Borel sigma field on those, as in random vectors taking real values in their components, and probably will largely be concerned with the case where they all take values in the same vector space Rd, or most commonly in the real line. But for much of what we're about to say, generality works just as well. Remember that sigma of xi denotes the smallest sigma subfield of f with respect to which xi is sigma of xi bi measurable. And of course we have a description of that. It's just the pullback by xi of the sigma field bi, meaning it is the set of all preimages under xi of sets bi, where bi ranges through the sigma field scripty bi. Now we define a collection of random variables like this xi to be independent if their sigma fields are independent, in the sense that we defined in the last lecture. That's what it means for random variables to be independent. Now, you might feel that the sigma fields associated to random variables are kind of nebulous objects and not fully understand what they tell us about the random variables. I know I felt that way the first 6 times that I saw this material. So let's go through carefully exactly what this says. What we're saying is that for every choice of bi's in the range sigma fields for these random variables, the events xi preimage on bi are independent. Okay? Now, what does that mean? It means that for any finite collection of them, so let's just, for the sake of notation, suppose that the set I consists of the indices from 1 up to n, we have that the probability of the intersection x1 preimage on b1, x2 preimage on b2, etc., xn preimage on bn, is equal to the product of those probabilities. Another way to write that, which is more common, is to say that the probability that x1 is in b1 and x2 is in b2 and etc. through xn is in bn is equal to the probability that x1 is in b1 times the probability that x2 is in b2 times etc. through the probability that xn is in bn. The probability that the random variables x1 through xn jointly take values in a collection b1 through bn is the product of their individual probabilities of being in those sets. We're going to explore throughout this lecture different ways of saying that same thing, but that is the definition of independence of random variables. In the last lecture, we talked about extending independence from classes to sigma fields, which worked in general provided that those classes were pi systems. Using the nice properties of preimage of measurable maps, we can extend the same idea in this context as follows. Suppose I have a collection of random variables taking values in some state spaces, and suppose that I have not the full sigma fields, but some subset of events in the range sigma fields that are pi systems. That is, each of these, a subset of that sigma field, is closed under finite intersection and generates the whole range sigma field as a sigma field. Then we can reduce our definition equivalently of independence of the random variables to saying that the preimages of the random variables on sets EI are independent when EI ranges through those subsets, scripty EI. We don't need to confirm it for all subsets in the BIs. This is certainly useful if we have real-valued random variables. This means we don't need to consider all possible Borel sets, which are very complicated in the range, but only restrict to any pi system that generates the full Borel sigma field. We'll look at that in a second, but let's prove this result first. So let's define Ci to be the pullback of EI by Xi. In other words, it's the set of all things of the form Xi preimage on EI, where EI ranges through the class scripty EI. We're going to show that those Ci's are pi systems that generate the appropriate domain sigma fields. So Ci is a pi system. Why is that? It's because of the nice properties of preimage. If I take A and B to be two sets in Ci, well, that means that they have the form Xi preimage on some set E and Xi preimage on some set F, where E and F are in scripty EI. And that means that the intersection of A and B is Xi preimage on E intersect Xi preimage on F, and the way preimage of any function works, that's the same thing as Xi preimage on E intersect F. Now E intersect F is back in EI because EI is a pi system. And therefore, this is the preimage of an element of EI by Xi, which is exactly to say that A intersect B is in Ci. So Ci is indeed a pi system. Now, what about the sigma field generated by Ci? So that's the sigma field generated by the pullback of scripty EI by Xi. But we have a nice result from an earlier lecture that you proved on your homework, that the sigma field generated by a pullback is the pullback of the generated sigma field. And by assumption, EI generates all of BI. So this is the pullback of BI, which is of course the sigma field generated by Xi. Thus, if this condition here holds, which says that all of these sets are independent, by the lemma we proved last time, if the Ci's are independent, then so are the sigma fields they generate, these guys, because the Ci's are pi systems, which tells us that these sigma fields are independent, which is exactly to say that the Xi are independent random variables. The converse is easy. If the Xi are independent, and therefore these are independent, then these subsets of those are, of course, independent as well. And so that proves this lemma. So, for example, suppose that all of our random variables are real-valued Borel random variables. We could take, for example, EI to be the set of half-infinite intervals from minus infinity up to t as t ranges through the real line. This is a pi system. The interval from minus infinity up to t intersect the interval from minus infinity up to s is the interval from minus infinity up to the minimum of s and t. And so it is again in that set, EI. So it's a pi system. We also know that it generates the Borel sigma field. I can take the difference of any two of these to get a half-open interval, and we know that the half-open intervals form a semi-algebra which generates the full Borel sigma field. And so this exactly fits the conditions of the lemma here, which means that for real-valued random variables, they are independent if and only if these sets are independent. From the definition, what that says is that we can characterize independence of real-valued random variables by this condition here. That is, the probability that x1 is less than or equal to t1 up to xn is less than or equal to tn is equal to the probability that x1 is less than or equal to t1 times up to the probability that xn is less than or equal to tn, which is, by definition, the product of the CDFs of those random variables at those different parameters t1 through tn. You might call this the joint CDF of the random variables. And so independence of real-valued random variables is equivalent to this product property. The joint CDF of the random variables is the product of the CDFs of the random variables. This product structure is very general, and in fact it has to do with the characterization in terms of the joint law of the random variables being product measure. We've talked about joint laws of real-valued random variables, but the same idea applies to general random variables like we're dealing with now. Suppose I have a collection of random variables that have values in different state spaces. I can put them together in a kind of vector and talk about the joint law of that. The joint law of that collection of random variables is going to be the probability measure on the product sigma field that is defined by the probability measure in the domain pushed forward by this map x to the product space. So just to be clear, remember that the product sigma field is the sigma field generated by all Cartesian products of sets in the individual sigma fields. And it is a sigma field over the product S1 times Sn, which is the range of this function. Now, in the case we're usually most interested in, if all of the state spaces are just the real line equipped with the Borel sigma field, then, as we noted, the product sigma field is the Borel sigma field over Rn. And so this corresponds with our earlier notion of joint law of random variables. One way or another, what we're saying is that the joint law of x is the probability measure on the product space defined by the measure of a product set B under mu x is equal to the probability that x is in that set B. The theorem, which characterizes independence now, is that in this general context, a finite collection of random variables x1 through xn are independent if and only if their joint law is the product measure of their individual laws. This follows very quickly from the definition. Let's take any collection of events bi in the range sigma field scripty bi and look at the probability that x1 is in b1, x2 is in b2, up to xn is in bn. Well, that's the same thing as asking for this vector of those random variables to be in the product of b1 through bn, which is by definition the law of x at the event b1 times bn. Thus, if the joint law is the product measure, then by the rectangular property of product measure, this will equal mu of x1 of b1 times mu of xn of bn, which by definition is the probability that x1 is in b1 up to the probability that xn is in bn. And so that tells us that x1 through xn are independent. So that gives us the reverse direction here. For the forward direction, if we know that x1 through xn are independent, then look at the probability that that vector of x's is in the product space. So that is, reading upward on the right, just the probability that x1 is in b1 and x2 is in b2 and xn is in bn. And because of the independence, that factors as the product that x1 is in b1 up to the probability that xn is in bn. Well, that's the individual law mu x1 of b1 times up to the individual law mu xn of bn, which, for product sets like b1 times up to bn, is the product measure on that product set. And so we've verified that the joint law on product sets coincides with the product measure. But we know that that uniquely characterizes the product measure. Alternatively, we can think of the fact that the set of Cartesian products like this is a pi system which generates the whole product measure by definition, and when two measures agree on a pi system that generates the whole sigma field, they agree everywhere. So one way or another, that gives us the proof in the other direction. Independence of random variables is equivalent to their joint law being the product of their individual laws. One quick consequence of that is that we can now relate this notion of independence of random variables to an earlier independence type notion that we developed a few lectures ago, uncorrelated random variables. Suppose I have two random variables x and y, both real valued, defined on the same probability space, and both L2, square integrable. If they happen to be independent, then they are uncorrelated. Their covariance is 0. Well, that's just a calculation now. The covariance is defined to be the expected value of the product minus the product of the expected values. But we can compute those expected values in terms of the joint laws of these random variables by the change of variables theorem. The change of variables theorem will tell us that the expected value of the function xy is the integral of little xy integrated against the joint law of x and y. Now, if those are independent, then this is the integral of xy against the product measure, mu x dx, mu y dy, and by Fubini's theorem, which applies because x is in L2 and therefore in L1 of this probability measure, and y is in L2, therefore L1 of that probability measure, this can be evaluated as an iterated integral. But of course, with respect to the inside integral for dx, y is a constant, so we can move it outside. In other words, we're noticing that this function xy is a tensor product function. And so this just becomes the integral of y mu y of dy times the integral of x mu x of dx. But those, again using the change of variables formula, are the expected value of y times the expected value of x. And so that says that this is 0. Independent random variables that are L2 are uncorrelated. The converse, however, is typically false. Being uncorrelated is strictly weaker than being independent. And we'll see examples of that at the end of this lecture.